This meeting is being recorded.
Welcome to the Fractional Calculus Seminar Series. Today we have Dr. Fabrizio Cinque, who is currently working as an expert in the Bank of Italy since November 2021. He received his MSc in 2020 and PhD in Statistical Sciences, Methodological Curriculum in 2024 from Sapienza University of Rome, where he has been tutoring for several times in graduate courses for stochastic processes and statistical inference. The core areas of his research are random motions with finite velocities, also known as telegraph process or continuous time random walks, point processes, pseudo processes, array functions, and fractional calculus for stochastic processes. We're very happy to have you here. You may please begin your talk.
Thank you for the introduction, and thank you all for the possibility. So today I want to show you some results that I obtained together with Professor Enzo Singer during the 2023 and 2024 studies. And they will concern the analysis of fractional Cauchy problems and the relationship with time-change stochastic processes. So we will see some prerequisites that we need to understand some results. Then we will go to some specific fractional Cauchy problems to obtain explicit solution of these problems. And then we will try to go in a further, more generalized setting and work out some what we here it's written stochastic composition, which recalls what happens when there is a time change stochastic process solution to a Cauchy problem. So first of all, the motivation of the first part of the speak and what, let's say, leads me to start studying this topic in further details. Here in the first row, you see the fourth order partial differential equation. This fourth order partial differential equation emerges while studying a specific type of planar random motion, so a specific type of random motion with finite velocity. I will say a bit more about this motion in an example right after some results. So actually, during a presentation at Sapienza University, a colleague and friend of mine asked us if we tried to deal with a fractional version of this equation. And that was the input for our study. So we tried to understand how to put the fractional parameter, how to put fractionality in this equation. And of course, we follow the usual guidelines. So we introduce a parameter ni greater than 0. And we obtain the fractional differential equation. Then the first step was to apply the Fourier transform in order to remove the dependency from the space variables, x and y, and we obtain such equation. Here, I'm sorry, it's cut, but there's nothing really interesting, and we will see again this formula incomplete. So at this point, our problem was to study a fractional equation in just the time variable of the type here. So in which we have a linear combination of operators of order ni times k, where k are integer and ni is our fractional parameter. And f, of course, it's a suitable function. Now, with the space in a multidimensional space, with the space variable, which can be multidimensional as well. Now, in which sense we are introducing the fractionality? We work with the Dzherbashyan Caputo fractional derivative, which is, I think, well known for the most of the audience. In here, we have the specific that the derivative it's inside this convolution type, in some sense, derivative, which is a particular case of the convolution type derivative, which we will recall also later. And so we have the derivative inside the integral differently from the Riemann-Liouville formulation of the fractional derivative in which the derivative is outside. Of course, in the case of the integer parameter, so in integer order, we recover the normal, classical, ordinary different derivative. Now, for the following, even though we will not enter in the details of the proofs of the statements, we will just follow. We'll just report all the several results, but we will not enter in the details of the proof. But it is very important in those to understand and recall how the Laplace transform of the Dzherbashyan Caputo fractional derivative works. Also because then we will try to use more complicated operators which somehow generalize this kind of effect in terms of the Laplace transform. And so here we have the Laplace transform of the fractional differential operator, and which returns here the Laplace transform of the function f minus a function minus, let's say, a sum in which appears the initial conditions of the Cauchy problem that we will need to deal with. And some tools that we will need to use are stable subordinators and their inverse. So very briefly, I will recall that a stable subordinator given a parameter alpha is a non-negative, non-decreasing stochastic process with stationary independent increments. That is a particular case of a Levy process. And it has a specific moment generating function, which is here given. And we will not see it, but some results may be also extended in the case of subordinator related to Bernstein functions, whose moment generating function is related in a similar manner, but instead of the function minus mu to the power of alpha, we will have a Bernstein function there. The inverse of a stable subordinator is nothing more than the first step, the first passage time given here. So we're looking at from the point of view of the time, according to the stable subordinator. And it's relevant for the proof. Again, we will not see these details, but it's relevant to keep in mind that the T-Laplace transform, so the Laplace transform with respect to the time of the inverse of the stable subordinator, has this shape. This is also important because during, let's say, our computation, we also derive this interesting formula, which is expressing the inverse of a stable subordinator of order 1 divided by n, with n integer, in terms of independent gamma random variables. Independent gamma random variables, so a very elementary object, probabilistic object, in which the time appears in the scale parameter in the denominator, meaning that as the time grows, the inverse also increase the variability. Now, another tool that we will need is the Mittag-Leffler function. We'll have the 3 parameters Mittag-Leffler function, or also known as generalized Mittag-Leffler function. We will also see the case in which gamma is equal to 1. In the case of gamma equal to 1, this term will is equal to 1, and we recover the 2-parameter Mittag-Leffler function, which has, and the generalized Mittag-Leffler function has this Laplace transform. And we also will need to use a multivariate Mittag-Leffler function, which was introduced some years ago in a paper of Saxena and others. And in here, we have the vector x, the variable x, which is a vector. And you can see that it has a sequence of series, but they all have the structure of a generalized Mittag-Leffler function here, except for the gamma terms. In fact, the gamma terms involves all the parameters, all the indexes of the series, and therefore it combined all these series. And it's relevant to see how the Laplace transform is done for this multivariate Mittag-Leffler function, because as you can see from here, it may be obtained, in particular this product and this summation show us that it may be obtained as the product of the Laplace transform of the generalized Mittag-Leffler function. And in fact, that's the case, meaning that this multivariate Mittag-Leffler function, it's actually the convolution of some generalized Mittag-Leffler functions. And this is used actually in the proof. Now, the first result I want to show you concern the explicit solution of the fractional Cauchy problems that we saw at the beginning. So let's a bit more in detail in the hypothesis. So we assume that some parameters lambda such that there is a polynomial, this nth order equation, which has which admits, of course, roots eta 1, eta m. Each eta has algebraic multiplicity of mj. This is relevant because later on we will see a result in which the algebraic multiplicity is equal to 1 for all the roots of the polynomial. And the result will change and it will turn much easier. The final result will be much easier. So we have this, which can be considered the characteristic equation of the fractional differential equation reported here in equation problem number 5. So here we have our main problem with some initial conditions in which this f are admitting the Fourier transform. That's mostly the requirement we ask for this kind of functions. Then the solution of problem 5, assuming that the roots of the polynomial of the characteristic polynomial are eta 1, eta m with multiplicity m1 and m, it's given in formula 6, which is actually a linear combination. As we can see, it's a linear combination, a finite linear combination of multivariate Mittag-Leffler functions. So what happens is that the arguments of this multivariate Mittag-Leffler function are the solution of the characteristic polynomial multiplied times t to the power of n, which is, as we all know, a very typical form for the Mittag-Leffler functions. And the parameters, those which were gamma in the previous slides, so these parameters are given by the multiplicity of the solution of the roots, of the solutions of the characteristic equation. So it is a linear combination of multivariate Mittag-Leffler function involving the solution of the characteristic equation. And this is the only element in which the solution, eta 1, eta m, are appearing inside the explicit formula of the solution. On the other hand, the initial conditions are appearing as the coefficient of this linear combination. And we also have a term in t, which is out of the Mittag-Leffler function, which is related to the maximum order of the fractional derivatives, this capital N times k. And I will not comment this specific KL, it's like just a technical issue in case. But I want to show you what happens in the case of a specific problem, how to relate problems with different fractional order. So as usual in probability, now we want to see what happens if we consider a problem of order n divided by n, meaning that the main differential equation has orders n divided by n times k, as always k which goes from 0 to n, and a series of suitable initial conditions. And we want to relate this problem, problem 7, keeping in mind the hypothesis about the algebraic multiplicities which were given above, to another problem, which is of fractional order just n. So in which the order of fractionality is not n divided by n, but it's simply n. And the result is that the solution of the problem 7 of order n divided by n can be expressed in terms of the expected value of the function solving a problem of order n, that I will comment in a second, time changed with the inverse of a stable subordinator of order 1 divided by n. So first thing to comment is the initial condition, which must be included in the problem solved by this f ni. In fact, the original problem had some initial conditions which must be recovered in the, let's say, increased problem, because ni, of course, it's higher than ni divided by n. And as you can see in problem 8, the initial condition of the problem of order ni are some equal to 0 and some equal, they recover the previous initial conditions. In particular, those which recover the initial conditions are those of index h, so the h derivative, where h is equal to n times L. So we recover the initial condition of the original problem just in those derivatives which have h equal, which are multiple to n. And we are always sure that these are always listed because this quantity, because the number of initial condition of problem 8 admits all the previous condition which were in problem 7. So here we have a stochastic subordination in the sense that we are subordinating the solution of the problem ni divided by n. We are expressing the solution of the problem of order ni divided by n as the solution of a different problem of order ni subordinated, so time changed in some sense, with a inverse of a stable subordinator of order 1 divided by n. Now, a particular case of this result is, of course, when we consider n equal to. In this case, the inverse of the stable subordinator can be expressed as equal to a reflected Brownian motion of parameter 2t of time. And therefore, we obtain a Brownian subordination of the solution of a problem of order ni divided by 2. By iterating this argument, we can also obtain the solution of a problem of order ni divided by 2 to the power of n as an iterated subordination with Brownian motions. Of course, we could obtain the same result by iterating, considering instead of 2 a different integer. So the result would be substantially the same, but instead of having this Brownian motion, we will have the inverse of the stable subordinator of order 1 over, I don't know, m, assuming that we are considering m to the power of n right here. Of course, these Brownian motions are all independent between each other. Another observation which must be done is that in the case of a previous problem, so I will recall a second, in this problem, if we assume all the initial conditions equal to 0 except the first one, then we obtain the above result, meaning this subordination, not only with the inverses, with the inverse of stable subordinators of order 1 divided by n, but for a general inverse of stable subordinator of order alpha, meaning that we can compute the solution of a problem of order ni times alpha, expressing it as a stochastic subordination, as an expectation of the solution of the problem of order ni, which now has easier initial conditions, of course, because they will be all 0 except the first one. Time changed with the inverse of a stable subordinator of order alpha in 0, 1. So in the case of initial conditions equal to 0, this subordination somehow is more powerful, and we do not restrict ourselves to indexes of order ni divided by n. Now, the second result about the result I was recalling before about the algebraic multiplicities equal to 1. It's, in my opinion, very interesting because it simplifies a lot, and it does not require, the explicit solution does not require the multivariate Mittag-Leffler function. So again, etas, the eta 1, eta capital N this time, are the solution of the characteristic equation of the problem 10. And in this case, we obtain a solution, an explicit solution, which is, again, a linear combination, but as I said, not anymore of multivariate Mittag-Leffler function, but of two parameters Mittag-Leffler functions. So functions which are rather simple to handle. And again, in the coefficient of this linear combination, it appears the initial condition, so the functions of the initial condition, in the initial condition, and a term which this time involves the eta. In the previous formula, we saw that the etas were just appearing inside the multivariate Mittag-Leffler function, while here they are also characterizing the coefficient of the linear combination. In this case, some particular cases are when we have, again, all the initial conditions equal to 0 except for the first one. And in this case, we recover a very simple formula because it's the linear combination of, there is here, first of all, just one sum, while before there was also a sum to the L, which were literally corresponding to the initial conditions. And here, of course, we lose it because we just have the terms L equal to 0. And so we have a linear combination of Mittag-Leffler function, which are literally the classical Mittag-Leffler function. So the basic, and this is the auto function of the fractional Caputo-fractional differential operator. Of course, if we set n equal to 1, we obtain a general solution to the integer order differential Cauchy problem, which now, of course, it is expressed in terms of the exponential functions and not anymore of Mittag-Leffler functions. And this is the solution to the problem in which the initial conditions are not equal to 0. And you can see, of course, that it simplifies a lot. Now, an application to come back to the motivation of this study. So, as I said, we started from the study of a planar random motion. Now, I don't want to enter in details of the planar random motion, but just to give you an idea also, because it's like a topic which I dedicated a lot of time. So just to give you a brief idea of what a random motion is, and then to see how we were able somehow to apply these results, this general framework we built in the specific case of our fractional motion. Now, random motion, in this case a planar random motion with finite velocity, can be expressed as an integral of a random velocity process. So you must imagine this V as a process which is representing a random velocity. In this case, the random velocity is taking values in plus minus C E1, which is the canonical vector of the space. So the vector 1, 0, and E2 is the vector 0, 1. So this motion, it's moving orthogonally in the plane, meaning it can go right, upward, left, or downward. And another way of expressing it, it's in terms, and the this process, here there are not the details, but this process involves also a point process. In general, we consider a Poisson process, and of course, for the derivation of the fourth order differential equation we saw at the beginning, we used the property of being a Poisson process. So we can explicit this integral as the sum over these steps counted by a Poisson process of parameter lambda. Each step has a length which is given by this difference, which equals the waiting times of the Poisson process. So the motion performs a movement with velocity v at time ti, at the beginning v0, for a certain waiting time, which is exponential, of course. And here in the plot, you can see some potential sample paths of this motion. So it's a motion which makes these segments upwards, to the right, to the left, and downwards. Of course, its support is inside the square, this square, the dashed square. And while studying the distribution inside the square, because we could separate the study on the above the border of the square, on the vertices of the square, so the points 0, ct 0, 0, ct, and so on and so forth, and inside the square. Now, when you go studying the distribution of this motion inside the square, thanks to the property of exponential displacements, we will obtain the fourth order differential equation that we derived at the beginning, that we started the talk with. And then we said we simply insert a fractional order Ni inside that equation, and by performing the Fourier transform, we obtain equation 12, which was the one which in the first slide was a bit cut. Now, equation 12 can now be solved. We can obtain the explicit solution of equation 12, keeping in mind some initial condition that we need to define. Now, for the sake of simplicity, here I've reported just the result, in which we assume the initial conditions all equal to 0 except for the first one. And so in practice, as we saw, we took equation 12, we studied the characteristic equation, we solved the characteristic equation, obtaining the four roots of this equation, which are eta 1, eta 2, eta 3, eta 4 here written in terms of this capital A, capital B. I don't want to comment the interpretation, let's say, of this result, but just to show a practical, in some sense, example of the theory above built. And assuming that the initial condition, this initial condition, which is actually inherited by the original problem of the planar random motion, and setting, for the sake of simplicity, the other initial condition equal to 0, we obtain this formula, which is quite elegant, since it is again a linear combination of the Mittag-Leffler function, and the coefficients are literally the product of the solutions which are not inserted as a variable in the Mittag-Leffler function. So eta 2, eta 3, eta 4 for the Mittag-Leffler function, eta 1, so on and so forth. Now, we cannot say that this is the Fourier transform of the time-changed planar random motion, time-changed with the inverse of a stable subordinator of order Ni, since actually the original problem, so the integer problem, had, of course, 4 initial conditions, and they were not all equal to 0. So to derive the right form of the time planar motion, time change with the inverse of a stable subordinator, would require to introduce those somehow those initial condition also in our reduced fractional problem. And of course, the solution, as we saw, would be much more complicated. Now I want to move a bit forward. So now we saw a specific fractional Cauchy problem of order Ni times k, where the operator was fractional Caputo derivative of order n times k. And I want now to go a bit further. We will not obtain, in some sense, explicit result, but we want to work by stressing this idea of time-changed processes. So here we define what stochastic composition means for us. And the simple way of seeing it is if we have two functions, f and g, and they are respectively the transition density of two stochastic processes, f and g, then the stochastic composition of these two functions is nothing more than the transition density of the composition of the composed process, f composed g. So here we have the time changed that we want to deal with. In general, we define stochastic composition, this integral, when the integral, of course, converges. And it's not said that what we're going to see has a probabilistic interpretation. Now we want to work, in fact, with a more general framework. We will see more details on the hypothesis of this system in the next of these problems in the next slide, but I want to give the idea now, which is somehow expanding what we did with the stochastic subordination in the previous slides. So we want to consider a problem, a Cauchy problem like 14, in which we have on the left-hand side a fractional Caputo derivative, and on the right-hand side a general, somehow we will see the hypothesis, some hypothesis on this operator, a space operator on the right-hand side, and of course satisfying some initial conditions. Our aim would be now, our interest is to understand if we can write the solution of this, let's call it space-time problem, meaning that it has fractionality, in some sense, generality in space and time. So let's call it space-time problem. In terms of the stochastic composition, in the terms we said before, we saw earlier, the stochastic composition of two functions. One which satisfy a space problem, which is the one involving a normal, a classical time derivative, but involving the space operator. Of course, we will need to understand this initial condition that we need. And the second one involving the time operator, so the fractional, in this case, fractional time operator, but we will try to extend here the fraction, the time operator. So we want to understand if we're able to find, in some sense, a space problem and a time problem whose stochastic composition of the solutions lead to the solution of the space-time problem 14. Now, to understand a bit more some hypotheses about the element involved. So we are working with functions which are going to 0 as x tends to infinity. And we want the space operator, so this capital OX, this OX, the space operator to somehow behave well with respect to the Fourier transform. So we want that there exists a sufficiently smooth function f, such that if we apply the Fourier transform to the operator, then the result is the product of this function f times the Fourier transform of the function on which we were applying the space operator. Some examples about this this class of operators are the Laplace operator, the fractional Laplace operator, which was actually the inspiration for this approach, thanks to a paper of Orsinger and Toaldo, in which they are dealing with some problems involving the fractional Laplace operator, which, thanks to the property 17, leads to some interesting results. But also, for instance, fractional Ries-Feller operator. Now, under the hypothesis 17, and assuming that there exists the Fourier transform of these functions fk, of these initial conditions, then the solution of the space-time problem can be expressed in terms of the Laplace Fourier transform, and the Laplace Fourier transform of the solution, so this calligraphic L represents the Laplace transform, and this calligraphic F, the Fourier transform, is expressed as in formula 18, which is a combination of the Fourier transforms of the initial conditions, and of course, this quantities of mu derives from the Laplace transform. Now, thanks to this result, we, of course, like with some computation, we can obtain that actually we can find a space problem and a time problem such that if we consider the stochastic composition of the solutions, we obtain the solution of the space-time problem. So what I'm saying is that we are proving, and the theorem in the other slides is saying that, but I rather prefer to show you rather than read it only, is again that the solution of this problem, assuming the hypothesis we gave, can be expressed as the stochastic composition of the solution to the space problem. So this solution, and now we will characterize the initial condition we need. So what are these initial conditions? Stochastically composed, in the sense we said before, to the solution of this time problem, which again we are characterizing now the initial condition. And the initial condition we need is that I can separate two main cases. The case in which the initial conditions of the original problem, of the space-time problem, are all equal to 0 except for the jth condition. And then in this case, we can assume that the initial condition of the space problem, G, is equal to this initial condition that is different from 0, while in the time problem, all the initial conditions, all these initial conditions, which are considering the time derivative, are equal to 0, and this H is instead the function having Laplace transform given by this quantity, which is related to the fact that we're using the Caputo-fractional derivative. This is the case in which every initial condition of the space-time problem is equal to 0. Now, if it is not the case, so let's say that in general they're all different from 0, actually everything which is in between these two options, we can set the initial condition H of the time problem, which is again the initial condition to the space, referring to the space at time to the space position 0, equal to 0. The initial condition of the time problem of the space problem, equal to the Dirac delta function centered in 0, and the solutions and the initial conditions of the time problem, the initial conditions with respect expressing the derivatives, the time derivatives at time equal to 0, they must satisfy this relationship in which we are comparing somehow the Fourier transform of the original initial condition with somehow the Laplace transform of the functions ak. So here also we must require the convergence of this quantity. One can consider space operator such that the real part of this function f is lower than 0, is negative, so that this is literally the Laplace transform of function ak. But this is not really necessary because we may have some ak which are decaying so fast that this quantity converges. And an interesting, so this is what we have, so we can express the solution of the space-time problem in terms of the stochastic composition of a solution to a space problem and a solution to a time problem with the initial conditions given in points A and B according to what the initial condition of the space-time problem were. Now, an interesting result is one can ask what happens in the case of the limit if n goes to 0. So in the case of n going to 0, the fractional derivative here in time would disappear. So we would have a problem which is actually just in space. And that's really the case. So assuming some hypothesis, of course, and a sufficient hypothesis that we can exchange the limit as n goes to 0 with the Laplace Fourier transform, then the solution, the limit of the solution, which we must assume exists pointwise, the limit of the solution solve a problem of the type 19, in which the left-hand side of the differential equation is literally the limit as n goes to 0 of the fractional derivative. And of course, we are always keeping in mind this hypothesis, which in the previous problems were not explicited, but we stated at the beginning that as the space goes to infinity, the function, the solution must go to 0. Now, I would like to show you also some slightly more general results. So now we discussed assuming a specific time operator. So the fractional Caputo, Dzherbashyan Caputo fractional derivative. But we can try to extend to this theory, these results, to more general operators, time operators. We must require, as we somehow asked the space operator to behave well with respect to the Fourier transform, we are asking now that the Laplace transform of this new time operator, capital O-T, behaves well. So the Laplace transform of this operator somehow behaves well in the sense that there exist these functions Ln, Lnk, which depends on the actually on the order of n, sufficiently smooth. Let's say that we can work, we can integrate, we can do some operation, and some operators that we will understand a bit below with the going more in the details what they're needed for. So there are these operators and these functions such that the Laplace transform of this time operator can be expressed as written into formula 20, meaning that, again, similarly to what happens, of course, in the case of a Dzherbashyan Caputo fractional derivative, when we apply the Laplace transform, we have a function depending on mu and the fractional order n, which in the case of the fractional derivatives is simply mu to the power of n, which multiply the Laplace transform of the function of interest minus this combination of functions involving mu and some operators calculated at time t0 of some operators applied to the function calculated at time t0, which this part of course refers to the initial condition. We will use the initial condition of the Cauchy problem. Examples of operators which are satisfying the hypothesis here are, of course, the Dzherbashyan Caputo fractional derivative, but also the Riemann-Liouville, obviously, they're related. But more in general, also the convolution type derivative. The convolution type derivative is connected to Bernstein function. I will not go into details, but I suggest to give a look in case if you don't know about this topic. It's extremely interesting. And also this type of operators satisfy equation 20. Now, the problem, the space-time problem that we want to study now, does not concern only the Dzherbashyan Caputo fractional derivative, but this more general time operator. In particular, we can assume this this equation involving the sum of operators, of time operators. This sum, it's not really creating difficulties, but we can introduce it for the sake of generality, like it still matters, of course. And again, our space operators. Now, the initial conditions, of course, must be given according to what our time operator requires. So, of course, if we use the Riemann-Liouville fractional derivative, we know that these operators will not be simple integer order derivative, but fractional derivatives themselves. So here we are assuming all the initial conditions that we need to have in order to be able to use also the Laplace representation of this time operator. Again, we're not going into details of the proof, but they're mostly based on Laplace and Fourier transform and manipulations of the result. And again, also in this more general framework, we can say that the solution of problem 21, so of this space-time problem, can be expressed as the stochastic composition of the solution of the space problem we saw before, which was involving only the operator, the space operator, and a time problem, which is not this one, of course, anymore, but it's pretty equivalent to that one, meaning that it involves the summation of the time operators. And of course, again, we need to set the initial conditions of these two subproblems. And again, we can separate the case in which we have only one initial condition of the space-time problem equal to zero, only one condition different from zero, sorry. And in that case, similar to the case before, all the initial conditions of the time problem, which are above here, they can be set equal to zero. The solution of the space problem can be set, must be set equal to the initial condition, which is not zero. And the initial condition of the time problem of the function at the origin of the space must be related to this function, which is connected, the Laplace transform of this function must be connected to the function associated with the initial condition, which was non-zero. On the other hand, if every initial condition, like in a more general case, we can set again the initial condition of the space problem equal to the Dirac delta function, this function h set to zero, and again to assume the equality between the Fourier transform of the original initial conditions and this sort of Laplace transform computed minus f of gamma, assuming that f is negative, of this function, which are actually the function we must set. So everything, let's say, returns in a similar manner, also involving a more general time operator. Now I want to conclude just giving a brief example of this result. In this case, we are dealing with problem 23, meaning that on the left-hand side, here we recover again the Dzherbashyan Caputo fractional derivative. So we have a linear combination of fractional derivative in the sense of Dzherbashyan Caputo with order ni I. So it's different from the previous one, let's say the previous part of the presentation in which we were having ni times k. but of course the result will read in a different way. And as a space operator here, we consider the Ritz-Feller operator, whose Fourier representation is here given. And the initial conditions here, for the sake of simplicity, we saw that it is much easier to work with the problem with zero initial conditions, except for the first one. So the first one is equal to the Dirac delta function, and here we have zeros. And so in this case, the corresponding space problem, that of course these two operators satisfy the hypothesis of the previous theorem, and now the corresponding space problem is expressed in terms of the Ritz-Feller operator, and we know the solution of problem 24. In particular, here, as you see, the solution does not have necessarily, according to the parameters alpha and theta, does not have necessarily a probabilistic interpretation, but we can give a pseudo probabilistic interpretation, meaning that we're working with we're working with real functions, so with real densities rather than non-negative densities like, as usual, probability. And in this case, let's say that the solution of problem 24 is known, and it is the transition law, it's the probability or pseudo-probability law of a skewed pseudo-process, or under some hypothesis of the parameters alpha and theta, we recover a probabilistic interpretation that is a skewed stable process. Time changed with an independent stable subordinator of order theta. So the solution of problem 24, it's already a time change process or pseudo process. In this case, our time problem, because of course we need to consider the space problem, but also study the time problem, which now will involve this combination of Dzherbashyan Caputo fractional derivative. So recovering the initial conditions that we derived thanks to the theorem, to the general theorem, we know that the time problem we need to study is the following one. And the solution to this time problem, to this fractional Cauchy problem, is also known or can be derived. And it is expressed as the inverse. It is given by the probability or pseudo probability also here according to the domain of Niais. If they are in 0, 1, we will have a probabilistic result. Otherwise, we will have a pseudo probabilistic interpretation of this result. So the function satisfying problem 25 is the pseudo probability law of the inverse of this linear combination of pseudo-subordinators or subordinators, stable pseudo-subordinators or subordinators according to the parameter of the domain of the parameter Ni, which is involving, the solution will be the inverse of this linear combination of stable subordinators, which is involving, of course, independent subordinators. So what we have at the end of the day is that the solution of problem 23 can be expressed as the stochastic composition of the solution of problem 24 and 25, meaning that the solution of this fractional problem with Dzherbashyan Caputo operators on the left-hand side and Ritz-Feller operator on the right-hand side can be interpreted, and it's equal to the probability, let's talk just in the sense of probability law of the of a skewed stable process, time change with an independent stable subordinator of order theta, and then time changed with the inverse of this linear combination of stable subordinators. And so just to summarize briefly what we saw, the two main results and idea, which I hoped I was able a bit to give to the audience, is that the first, let's say the first part concerned the explicit results about a problem, a fractional Cauchy problem involving a specific type of operator with specific orders. So Dzherbashyan fractional Caputo derivatives of order ni times k. And here, of course, keeping in mind the initial conditions, which reveals, of course, to be extremely important in everything we showed. So in the first part, we wanted to derive some very explicit results about this kind of problems 27. And then, of course, we recovering some ideas, in particular this stochastic subordination, we try to extend this concept, trying to express the solution of a more general problem, as in Formula 28, in terms of the stochastic composition of the solutions of two subproblems. Those we saw, space problem and time problem, which were involving, in the case of the space problem, the space operator, but on the left-hand side, just the ordinary time operator, time derivative, and the time problem, which on the other hand was involving the time operators, and on the right-hand side, just minus the space derivative. Of course, we would like to go further into this topic. In particular, one of the most interesting thing would be, in my opinion, to understand how much we can stretch, in some sense, the hypothesis of the space and time operators, how much we need to base the results on the Fourier and Laplace transform. So if we can extend the families of operators for which this kind of stochastic composition of the solution can be present. And here are some main references, but of course there are much more which you can find inside these papers. And I thank you for the attention.
Thanks, Fabrizio, for the nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen. Yeah, I see a question by Lorenzo. Lorenzo, please go ahead.
Can you hear me? Yeah.
Yes.
Okay, so I will thank you, Fabrizio, for this nice talk and also for these nice topics. And I would like to ask you if can you repeat because I didn't get on slide 17. You have an integral describing with AK inside. Yeah, exactly. And yeah, I didn't get this f of gamma inside. What is that f of gamma? If you can repeat that.
Okay, this f of gamma is related to the space operator which we are working with, meaning that we assume this hypothesis. I know the symbology maybe all look the same. It's like, the idea is that we're working with the space operator, which when we apply the Fourier transform, simply reproduce, this application simply produce the product of a function f, which is a sufficiently smooth function, so that we can integrate essentially that thing, that integral, times the Fourier transform of u. And then this function f, as you notice, it appears here. And what I was saying is that, let's say a further detail was that in order to be somehow sure of the convergence of this integral, but I remember that we are trying to understand the conditions on the AK. So our object is to understand which kind of functions AK we can choose, and it's those satisfying this equality.
Okay.
But in general, this f, we can assume it with the real function lower than 0. So this is literally the Laplace transform of AK computed in the value f minus f gamma, which may be an interesting representation of this formula.
Yeah. Okay, thank you. And also for the you told about that this problem in equation 21, maybe the slide later. For these also for the examples you show at the end, that sometimes you can have a stochastic interpretation and other times you cannot. So if there are, which could be like the problems of, or if these are problems related to like the operators involved, or I don't know, in
Okay, yeah,
something.
this is also a very interesting question, and I would say rather I don't have a clear answer.
No, sure. Let's say in general, what
Yeah.
if you met some explicit problem, or which could be in general, I don't know.
Okay, unfortunately, in some sense, most of the cases we dealt with were involving either the Dzherbashyan Caputo fractional derivative or the generalization I slightly talked about, this convolution type operator. And in that case, so here we would have this kind of operators. And in that case, we would have a probabilistic interpretation in terms of subordination, of time changing with the inverse of a stable subordinator related to a Bernstein function in the case of this convolution type derivative, which is somehow the most we tried. So I cannot go after that. I don't know really, because of course another point would be to understand which is completely, in some sense, the class of operators satisfying hypothesis 20, and how to extend it, as I said at the end, if it's possible to release this hypothesis. And these are still open questions, in my opinion. And according to the space operator, also, I don't know exactly, I don't have exactly an answer for which is the line which separates from probabilistic interpretation and pseudo-probabilistic interpretation. As you saw also here, the pseudo-probabilistic, let's say the non-probabilistic interpretation already comes by using this kind of space operator. So the interpretation being probabilistic or not, it's not just on the time operator, but also on the space operator. Unfortunately, I cannot give a precise line about this kind of examples.
So it could be also a way how the fractionality in time and the fractionality in space could interact. Maybe it could be something also about the both operator you are using, for example.
Probably yes. Probably yes. Also because, again, even just considering problem 24, which is non-fractional in time, this is already itself a time-changed process. So as it's written here, as I said, it's already a time-changed process. So, but in this case, it's time-changed with with an independent stable subordinator. But probably assuming a different space operator, one may obtain a skewed stable process, time change with a non-probabilistic object. So this is a very interesting point. Like it would be interesting, of course, to define a border of these two.
When you can have it, when you cannot. Yeah, sure. That's okay. So thank you very much for this.
Are there more questions? You can unmute your mic and you can ask your question if you have one or any comments. I guess no. So this is a good point to close this talk here. Thanks, Fabrizio, for joining us today and for the nice talk. It was very nice to have you here today.
Thank you for the opportunity.